Everyone, imagine this. In a modern factory, robotic arms swiftly and precisely grasp components. Automotive parts are measured with micrometer-level accuracy, and product assemblies are perfectly aligned. How are such seemingly magical operations achieved? The answer lies in industrial vision endpoint calibration technology, a silent but critical enabler in advanced manufacturing. Let's unveil the mystery. This lesson primarily covers the following topics. It is hoped that through this lesson, you'll be able to attain the following learning objectives. Endpoint calibration plays an essential role in various stages of industrial production, significantly improving accuracy and efficiency. Common application scenarios include 1. Part localization and grasping. In automated production lines, robotic arms must accurately grasp parts on a conveyor belt. Endpoint calibration establishes a transformation relationship between the image coordinate system of the industrial camera and the coordinate system of the robotic arms and effector. Once the camera identifies the part's position and orientation in the image, it is converted into the robotic arm's coordinate system for precise grasping, such as in the micropart handling in 3C product manufacturing. 2. Dimensional measurement and quality inspection. Parts must be measured to ensure compliance with dimensional standards. Endpoint calibration converts image information into actual physical dimensions, enabling high-precision measurements of part length, width, hole diameter, etc. For instance, in the manufacturing of automotive parts, the dimensional inspection of key components such as engine blocks is carried out to determine if they are qualified. 3. Assembly operations. Precise alignment is crucial during the assembly of complex products like electronics and automotive components. By using endpoint calibration, the vision system can identify the position and orientation of the parts to be assembled, providing accurate guidance for robots or automated assembly equipment. This enables precise part assembly and improves both assembly quality and efficiency. 4. Defect detection. For surface defects like scratches and cracks on metal plates, or bubbles and deformations on plastic products, endpoint calibration ensures accurate defect localization and sizing. By converting image coordinates to physical coordinates, the system quantifies defect information, enabling timely detection and intervention. 5. Printing and packaging. In the printing industry, endpoint calibration ensures print registration accuracy and color consistency. In packaging, it enables product positioning and counting to ensure precise and consistent packaging, such as monitoring the position and quantity of medicine boxes in pharmaceutical packaging. 6. Welding operations. In automated welding, endpoint calibration enables the vision system to recognize the location and geometry of weld joints accurately. This guides welding robots for precision welding and improves welding quality and reduce manual intervention. Often be seen in automotive body and steel structure welding, among other scenarios. 2. Principles of industrial vision endpoint calibration. The principle of endpoint calibration in industrial vision is to establish a mapping relationship between image coordinates and world coordinates, and solve for the transformation matrix between them, thus realizing the conversion between coordinate systems. The principle includes 1. Coordinate systems and correspondence points. In industrial vision systems, 2 coordinate systems are involved, the image coordinate system and the world coordinate system. The image coordinate system is measured in pixels and used to represent positions of objects and images, while the world coordinate system corresponds to actual physical space and is associated with devices like robots or robotic arms. Endpoint calibration requires acquiring at least n pairs of corresponding points between the image and world coordinate systems. These corresponding points represent the same physical locations or feature points in both coordinate systems. 2. Transformation types and degrees of freedom. The relationship between two planar coordinate systems can be described by different types of transformations, such as Euclidean transformation, similarity transformation, affine transformation, and perspective transformation. Similarity transformation has 4 degrees of freedom and requires at least 2 pairs of points. Affine transformation has 6 degrees of freedom and requires at least 3 pairs of points. Perspective transformation has 8 degrees of freedom and requires at least 4 noncollinear point pairs to solve for a unique solution. 3. Optimization and accuracy improvement. In real applications, noise and other factors can interfere with the calibration process, making the calculated transformation matrix less accurate. To improve calibration accuracy, methods like iterative reweighted least squares or RANSAC can be used to optimize the transformation matrix. There are many successful cases of endpoint calibration in practical applications. Here are some specific examples. 1. Wind turbine blade cutting guidance. In wind turbine blade manufacturing, the Deep Vision SR7400 laser 3D profile sensor, combined with 3D camera guidance and 3D calibration algorithms, uses endpoint calibration tools for hand-eye calibration. By calculating the transformation matrix between target space coordinates and robotic arm coordinates, it transforms the camera pixel coordinates into the robotic arm's spatial coordinates, guiding the robot to cut the blades with an accuracy of up to 1 millimeter. This technological breakthrough demonstrates China's proactive approach toward its dual carbon goals. High-precision cutting technology not only improves the manufacturing efficiency of clean energy equipment, but also embodies the spirit of craftsmanship in the new era, driving green development through technological innovation and showcasing Chinese wisdom in global energy transition. It reflects the sense of mission and responsibility of scientists and engineers for national development. 2. Bolt tightening for loaders. A major construction machinery company introduced a 3D vision system for the manufacturing of loaders. It locates bolts on the frame side plates and guides a gantry robot for tightening. Using endpoint calibration, the bolt centers are accurately positioned, ensuring that the tightening gun aligns correctly. A single image can locate all bolts on one side of the frame, greatly improving assembly quality and efficiency. This vividly illustrates the transformation from made in China to intelligent manufacturing in China. The deep integration of automation and AI reflects the modern interpretation of values like honor and labor, greatness and creation. 3. Coordinate calibration of 5G base stations. In the major domestic research project on unmanned monitoring systems based on the integration of BeiDou and digital twin technologies, coordinate analysis and calibration of 5G base stations are carried out using BeiDou and 3D laser scanning technologies. By combining indoor and outdoor measurements and applying endpoint calibration and related methods, centimeter-level positioning accuracy is achieved, meeting the precision requirements for the future integration of BeiDou and 5G positioning systems. Everyone, this achievement is China's pursuit of scientific and technological self-reliance and self-strengthening. The handshake between BeiDou and 5G breaks through foreign technological monopolies and powerfully proves the profound truth that core technologies cannot be begged for, bought, or borrowed. 4. Multi-camera calibration. A patent by Hefei June Division Technology Company Limited describes a camera calibration method based on support vector regression. Multiple cameras are installed to capture the same spatial region, and the calibration board is moved multiple times. One particular placement of the calibration board is chosen as a reference to establish the world coordinate system. Using endpoint information, this method improves calibration precision and avoids overfitting, making it suitable for complex multi-camera calibration scenarios. This patented innovation exemplifies the strong synergy of collaboration between academia, industry, research, and application. By translating laboratory theories into practical industrial applications, researchers have taken a problem-driven approach to break through technical bottlenecks, avoiding the pitfalls of academic isolation and the reliance on unoriginal copycat solutions. Such a pragmatic approach to innovation provides a compelling model for nurturing top-tier engineers in the new era. 5. Robotic grasping. In robot vision-guided object picking, the 9-point calibration method is used. The robot picks the actual workpiece from 9 positions, capturing 9 images, and these are input into the 9-point calibration program. Using the robot's coordinate system as the reference, a unified coordinate system between the vision system and the robot is established, enabling accurate object grasping. This practical application of 9-point calibration can be likened to the personal growth of young individuals. From identifying the correct coordinates to precise execution, it not only requires rigorous training in technical standards, but also calls for the practical wisdom of integrating knowledge with action. It reminds us that in the age of smart manufacturing, we must develop strong technical competence and systematic thinking to shoulder greater responsibilities in everyday roles. Everyone, today we have explored the industrial vision endpoint calibration technology in depth, from its wide-ranging applications across industrial production to its fundamental principle of coordinate system transformation, and finally through real-world successful case studies. I believe everyone has already gained a comprehensive understanding of this technology. It's hoped that in your future studies and careers, you will flexibly apply endpoint calibration technology and contribute your strength to the intelligent development of industrial production. That concludes today's lesson. See you next time.